Hello guys, so today we are here to solve this very informative problem called coin change 2. In this problem we are given an array of coins, integer array of coins and an integer amount. So the two inputs are integer array of coins and integer amount. Okay, and we need to return the total number of combinations that make up that amount. We need to return the total number of combinations that make up that amount. Okay, so in this problem, basically we are given an array. Let's see this example one. In this, we are given an array and a amount, and we have to return that how many ways we can, add those coins. One coin can be added multiple times. Okay, how many ways we can use these coins to get this sum. Okay, so here one can be added 5 times, one can be added 3 times, and then two can be added in that, making up a total of 5. Then two can be added 2 times, and then again we can go back to 1. So these are the several, one coin can be added multiple times. Okay, fine. So we need to come up with a solution that, solves this problem. Okay, so it should return the total count. Okay, to get the total count, what we can do here, that we can write private and count is equal to 0. So this, by doing this, we are making count a global variable. Okay, and then what we are doing, that we are going to call one backtrack, and in this we are going to pass the coins, the amount, and the index of the coins, which is at first it is 0, and then we'll be returning the count. Okay, 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 like this, and then private void backtrack. Okay, so in the backtrack we will return, put some, terminating condition over here. Okay, and then we'll write else. In the else, what we'll do, we'll write backtrack of points, then amount. So at every given, at every coin, we have two choice. Either we can take one in that sum, or we can skip one from that sum. So we have coins, and then we have amount, and then we have the index. So if you are skipping that, then we can get ahead with that index. Let's say index plus 1. Okay, but if the coin under consideration at the given index is less than equal to amount, then in that case you can write backtrack of coins, amount, index, and that coin can be considered again when if coins is still smaller than the remaining amount. So we have to subtract this, coins and index. Okay, now our thing is that when we are going to terminate this process, so we can terminate this process when index is greater than equal to coins dot length. I mean to say when the coins is over, and if amount is equal to 0, we are subtracting from it and amount is becoming 0. Then what we are doing count plus 1. Directly we can say plus count return. Okay, so With this, we have our solution. And now if we run this, so here we have some problem. What is that? Oh my, we have not declared the parameters. And index like that. Yes. So this is a very basic backtracking solution for this coin change 2 problem. And we are making multiple coins calls in this problem at line number 17 and at line number 19. Multiple calls are there. And because multiple calls, since there are multiple calls, the time complexity of this is exponential. So I'll put it in comments over here. As there are multiple backtracking calls in the solution, the time complexity of the problem is let's say 2 to the power n. Okay, so this is the problem with this. We know that this is going to take too much time, and it may not be sufficient for some test cases. Knowing this, we'll try to submit it, knowing it fully well that some test cases where the um, values of either coin or amount is too large, we'll be running out of time. So let's see whether we get we are getting TLE. Okay. So I can prove that this solution is not this solution, this way of the way of writing the solution is not wrong. If I just decrement this amount to 300 and then again run this solution. So see, for 300 it is accepting. If I make it 350, will it accept? Let's see. For 350 also it's accepting. Perfect. That is good. Now let's make it around let's say 380. So this is at 380, it is returning time limit exceeded. If I make it as let's say 360, is accepted. 370. 370 is daily. Then let's do 365. So 365 is also getting accepted. If we do 368, really 366, 366 is DLE, 365 is accepted. Okay, now 365 is also showing DLE. So what we can do to pass this? So one thing that we can do is that, we can sort this points array. Okay. So this will sort in ascending order, which is of no use to us. We want it to be sorted in descending order. To sort it in descending order, what we can do, int I is less than points dot length by 2, and temp is equal to points of I, points of I, okay. So we will again take this. Okay. So this will reverse sort, and then again we are passing it. So let's see, this time we'll be, passing 370. So clearly 370 was not passing. What is happening now? Again, it's TLE. 365. Now I think everything is going TLE on. Okay. So this solution is correct, but it is not efficient, and we need to make it efficient. The, the reason why it is not efficient is because we are making within, single call, there are two recursive calls happening at line number 24 and line number 27. And when we are exploring the different scenarios, see what is happening, that at every amount, we are checking whether the given coin can be used or not used. If we are not using this coin, then we are going to, use this call. If we are going to use the coin, then we are going to use this call. Why we are not incrementing the index? Because as long as the coin is less than the amount, less than equal to the amount, we can use the same coin. Okay. So this is the major thing over here. Okay. And if you are skipping the coin, we are incrementing the index, and index represents the index of the coins array. Okay. So these are the two things with this problem. Now, what I'm going to do here, that I'm going to make this problem, I'll memorize the solutions, memorize the, solutions to previous problems, so that we don't have to do a recursive call. And instead of doing a recursive call, we'll be, doing a lookup in that memo table. And that lookup will be, storing the result of the subproblem. And that result will be using further down in our process. And that will help us to get the correct answer. So with that, what I'm going to do, that instead of this int, I'll, write one int double array memo. Okay. Let's initialize this memo here in this. Okay. Memo is equal to new int points dot length, like this, and then this amount plus 1, like this. And for int array memo, mem of memo. Okay. And in this arrays dot fill, mem of -1, like that. We are initializing every element of this array with this thing. And then at the end, I'm passing here memo. Okay. And so this memo will be returning some result while solving each and every sub problem, and will be, using this to get the answer. So now, since we are returning some value from this, making this as int, return type int, and then we'll make this int array memo like this, and see, earlier this was the one case when we are getting at the leaf. So once the index is greater than or equal to const.length and amount is equal to 0, this was the leaf of the backtracking state space tree. And at that point, whenever the leaf, the amount at that, whenever at the leaf, the amount is becoming 0, we are incrementing the count. And that is how we are, getting the value of, number of leaves, at which the amount is equal to 0. We are incrementing the count. And there we are, those are our solution set for our backtracking solution. Now, if we come out of this, I meant to say, the conditions are, like this. So we'll take this out. If amount is equal to 0, then not doing this will be, return 1. Okay. If index is greater than or equal to this, or amount is less than 0, then in that case, we'll be returning 0, like this. Okay. And then we'll be putting one check here, that if memo of index amount is equal to -1, like this, make it as LC also. Then backtracking will pass the memo here also. Okay, and we'll store the result of this in memo of index of amount. Okay, and this memo index amount is for the same index and amount. So the result of this call and the result of this call are happening for the same index amount. That's why we are doing plus equal to here. Okay, so whatever is the result in this number of ways that is stored in for this memo index amount, to that the result of this call will be added, and that's what we are doing here. Memo index amount plus is equal to. Okay, and at the end, what we can do here is that we can do a return memo of index amount. Okay, so I hope things are clear to all of us, and let me just try to run this and see what is the output that we are getting. Okay, oh my goodness, I have not passed the memo here, so I have to pass the memo over here. Perfect. 350. Now I am getting belligerent, and I am going to pass 700. 350 plus 350 is 700. Let's see what's happening. My goodness. So see how much efficiency memoization adds to our solution. Let's go one step further and do it, for 900. that is also passing. Now let's go one even more, you know, 1000. Perfect. So see, memoization is so powerful that, previously our solution was, struggling to pass test cases for the amount of 350. But, after memoization, even 1000 is, we are doing it, just like anything. So this is the benefit of memoization. And if there is any doubt, any problem, any such anything, please let me know. I'll, answer those doubts in the comment section. Uh, so till then, happy coding. Stop stopping yourself, and first and foremost thing, that be kind to your mind. Thanks a lot. So let me just submit this. Perfect.